Glad you told me, because I thought I was recording.
I thought that you were doing the little diagram first and then we're going to start recording.
How many states do we have? 4. A, B, C, D. I'm going to code the state, state A, give it the code 00. Notice I used 2 digits without saying anything. If you recall from last class, 2 to the number of states, number of flip-flops, should be greater than or equal to the number of states. So I have 4 states. So 2 to what power is going to be greater than or equal to 4? X will have to be 2. That's why I'm using 2 digits for the coding of the states. That will cover all the possibilities. If I have one more state here, 5 of them, I will have to use how many digits? 3. And maybe some of them might be unused state. So state B here, I'm going to refer to that as 01. State C, I'm going to refer to that as 10. And state D is going to be my 11.
Does it record your voice as well as video?
Yeah. Well, you never watched the videos? Oh, yeah, it records everything. 00, 01, 10. I sound actually wonderful on it. So make sure you listen to it. 11. Yep, when you listen to it, you'll see it's soothing and put you to sleep.
I was going to say, put it on every night and then in the morning you're still going.
Yep.
Gotta want to wake up.
Yeah. Now, so I'm going to use Q1 and Q2. So I'm going to call this one Q1, the one on the left, and I'll call this Q2. I need to have 2 flip-flops. Number of flip-flops, which says 2. Oh, scarf and coat. You got an interview?
No.
Okay. You just want to look good, that's it. Now, external input. We only have one. We'll call it X. That's these guys, the 0 and the 1. We don't have any output, because I don't see slash given the output 0, 1. So no output. I don't have to deal with that. Let's decide what kind of flip-flops we're going to use. Let's mix and match. Last time we used what? JK? So today I'm going to make the first flip-flop. Well, actually in the lab. That means an extra chip on the board there. Yep. Just thinking which might be probably the easy. What did we use last time? JK?
JKs are what we did yesterday, like when we made it all.
Yep.
That was a JK. But we also went over SRs
Yeah.
and Ds.
Well, let's use SR. You know what? I'll have fun. It won't be a lab one today. This won't be the lab because I got to use 2 different. I'm going to make the first one Q1. I'm going to make it a D flip-flop. And Q2, I'm going to make that a T flip-flop, just to be different. I'm going to mix and match. I was about to use SR. I'll use them for the next example, SR. So I'm deciding all the stuff we're going to use. T flip-flop, D flip-flop. Before I get to them, let's go back and see what the truth table for your D and T flip-flop, if you remember from before. Where are they? One of them actually on page 376 in our book. Let me put the T flip-flop, the truth table for it. Because we have to come up with the excitation table. T flip-flop, the way it works, T stands for toggle. The current state and the next state. The asterisk is the next state. What will happen? If T is 0 and the current state is 0, the next state is 0. If T is 0 and the current state is 1, you stay at 1. Basically, the way it works, the T flip-flop, if you remember, if T is 0, everything stays the same, no change. And if it's 1, what happens? You toggle, right? Toggle means you flip. So when T is 1, if this is 0, you flip it, that becomes a 1. When T is 1 and this was 1, you flip it, that becomes a 0. So let's come up with the excitation table. Let's see what will happen. I'm going to do the reverse here. If you know Q and you know the next state, can you tell me what T should be? From 0 to 0. From 0 to 1. From 1 to 0. From 1 to 1. Let's think about it. Let's look at this case and that case. What happened to the next state in relation to the previous state?
Same.
Stayed the same. That means T will have to be what? 0. This one, what happens as it goes from 0 to 1 and 1 to 0? It toggles, right? T is 1. That's your excitation table. If you know the current state and the next state, you can figure out what T should be. Let's look at the D flip-flop, data flip-flop. It follows the data. That's where the name came from. In our book, that was page 373. D, Q, Q next. Bless you. 0, 0, it's 0. 0, 1, it's 0. 1, 0, it's 1. 1, 1, it's 1. The D flip-flop. The same as D. When D is 0, you get a 0. When D is 1, you get a 1. So here we go. Q, Q naught, and what is D should be? 0 to 0. If you go into 0, D will have to be what? 0. From 0 to 1, D will have to be 1. 1 to 0, D will have to be 0. And 1 to 1, 1. Those are the excitation table. That's what I need for the rest of the problem. So last time we looked at the JK excitation table. This is the T, this is the D. The only one left, that's R. We'll do that next time, or next example. Maybe I'll use a graph paper because I can line things nice and neat here. Damn it, I forgot to bring highlighters with me. Different color highlighter. I put them in a bag and left them sitting in my office downstairs. You do? I just need 2 colors. I have a yellow one. I just need one more. It makes it easy on the eye when I'm looking for it. Sure. Thank you. So let's look and see. I'll make sure this is nice and neat. Thank you. I don't know if I need all of that, but I figure go ahead, put a line there. Let's look and see our inputs. We have, I'm going to write here the current states. current state, and I have two of them, Q1, Q2. So this is Q1, this is Q2. These are the current states. And we also have the external input, which is X. I need to look back at this one. So let me list my cases. I could be a state 0, 0. My input could be 0, or 0, 0. My input could be 1. Let me look at the next state. We'll call that Q1 asterisk and Q2 asterisk. If I am at 0, 0, looking at that picture, my input is 0, I go to B, which is what, 0, 1? But if it's 1, you go where? To 1, 1, right? If I am at state 0, 1, my input is 0, or 0, 1, my input is 1. This is this one. If it's 0, I go to A, which is 0, 0. If it's 1, I go where? To C, which is 1, 0. Next, state 1, 0, my input is 0, and 1, 0, and my input is 1.
Q2 is the D, right? The T.
What is it? 1, 0. If it's 0, we go to 0, 0. If it's 1, we go to 0, 1. And the last one, state 1, 1. My input is 0. 1, 1, my input is 1. 1, 1, my input is 0. I go to where?
1, 0.
1, 0. 1, 1, my input is 1. I go to where?
1, 1. You stay there.
Yep, you stay there when it's 1. Now, did we decide which flip-flop? Q1 is the D flip-flop, right?
Mm-hmm.
And Q2 is the T. So, here we go, the D flip-flop. What I'm going to do, I took Robbie's color markers. I'm going to look at Q1. That's why I want the color, so I can look and see. That's the current state. That's the next state. And this is where the answer is going to go. So let me look at the excitation table for that, for the D flip-flop. That's this one, the bottom one. Let's see if you can see it. Yep. Can even go higher. A bit higher. 0 to 0. According to this one, you want D to be what? 0. 0 to 1, you want D to be what? 1. 0 to 0, I want D to be 0. 0 to 1, I want D to be 1. 1 to 0, I want D to be 0. 1 to 0, D is 0. 1 to 1, D is 1. 1 to 1, D is 1. So D1, or that's the flip-flop. The first flip-flop is a D. The second flip-flop is a T flip-flop. I call it T2. 2 means the second flip-flop. And for that, again, we'll use a different color so I know where to look. color makes it easy on the eye where to look for them, especially when you have a lot of these. So this is the T flip-flop. Let's look at the first one, 0 to 1. That looks like a toggle. 1. 0 to 1, that's a toggle. 1. 1 to 0, that's a toggle. 1. 1 to 0, that's a toggle. 1. 0 to 0, that's the same. 0. 0 to 1, that's a toggle. 1. 1 to 0, that's a toggle. 1. And 1 to 1, that's the same. 0. So I got all the pieces.
I have a question.
Yes.
I'm just a little confused on how you got those numbers from that map.
What numbers?
Like what you did just.
This column?
How you get the rows? How you got the rows? The Q1, Q2,
Here?
Q1 asterisk, yeah.
I'm just listing all the combinations. Your state 0, 0. Your input is 0. Right?
Were you here for this?
No,
That's why. If you look at this, when you have 0, 0 here, that's at A. When you have another 0, it's B. And then when you have 1, it goes to B.
this
That-
is 0.
That came from the state diagram here.
Okay. Well, I knew that it came from that diagram.
Yeah,
Just
yeah.
go on.
So now I'm just going to do a kmap for this, a kmap for that, and I can go and build them. Let's do a kmap for D1.
Do you ever do timing graphs or what have you?
We could. We did that for homework. We did that last time. We just followed it, actually. The last homework I think I gave you, Stephen, we did some timing diagram, I think, like this, where you have to go through that.
No. It was like you put arbitrary input in, and it shows the behavior of the system. It's like the graph version of the state diagram.
No. No, we just,
It's like really easy to
Yep.
like pop right out of you.
yep. So now let me do a kmap for D1, a kmap for T2, then we'll build it, and that circuit is ready to be designed. My inputs are Q1, Q2, and X. My current state and X. So here's D1. 0, 1, 0, 1, 0, 0, 1, 1. That's easy to read. Group this one, group that one. D1 is going to be what? Q1, Q2, or Q1 naught, and X.
Can you explain that?
Which one?
What you just did.
Kmap. Took D1, put them in the map, and read the map. That's one group, that's the other group.
What does that prove?
Huh?
What does that prove?
No, that's the input. I'm going to be designing them.
Okay.
Basically, do you remember what we did with like A's, B's, and C's? We're just replacing it with Q's and X's.
Yeah, no, but I'm having trouble because it's a sequential system. It's not like, just a regular key weights or whatever.
You'll see in a minute. Q1, Q2, and X. One, 1, 0, 1, 1, 0. To read that, I can take the 4 here, and that looks like what? Q1 naught? I can take these two ones, Q2 X naught, and I can take this one with this. And that'll be what? Q2 naught X. Steven said, what are these things? What do they represent? These are actually going to be the input to my flip-flop. Now I have two flip-flops. One is called D flip-flop, the first one. The second one is T flip-flop. I'm going to build them now. So if I'm in the lab, I have two chips because they're different flip-flop. The one in the back, this end, is going to be the D flip-flop. So it will look like this. Leave some space there. It has one input, that's the D. Well, it has a clock there too. They usually have a reset and preset. We talked about them last class. So this is the input, that's D1. That's number one, the flip-flop. It has two outputs. This is Q1 and this is Q1 naught. There's a clock here. And again, it depends on the flip-flop. It could work on the rising edge or the falling edge, the leading edge or the lagging edge, the trailing edge. So we have another flip-flop here. So this is my second flip-flop, which has two outputs and one input. The input to that is called T. This is number 2, that's why I labeled T2. It has two outputs, we'll call them Q2 and Q2 naught. What these represent, when you say what's D1 here, this is the input going to this. And what shows me it's actually an OR gate. Let me just minimize this line, it's too long. It is an OR gate and what's attached to that OR gate? Two AND gates. See them? One is it's going to have a Q2 ANDed with Q1. And the other one is going to be what? Q1 naught and X. So if this is X, which is my input, that's my external input. Let's make that my external input here. I don't know if I needed. I'm going to have an AND gate. And what's going to it? X and Q1 naught. This is X. And this is Q1 naught. You take this one, loop it around, and attach it right here. And we have another AND gate here. And what's going to that? Q1 and Q2. This is Q1. And there's Q2. Bless you. I don't need that. So that's the first flip-flop. Now the second one is going to have an OR gate with three things going to it. One of them is what? Q1 naught. That's the input from here. Directly, see it? So let me take Q1 naught, move it up there higher. And feed it to this one. The other one, Q2 and X naught. Where's Q2? Right here. So I need an AND gate. Q2 and X naught and Q2 naught. Should have raised this a little bit higher. Will look a little bit nicer. I didn't plan it right there. I have another one here. That's an AND gate. And we say what's going to it? Q2 and X naught. Now X naught, I got to take it from here. There's the NOT gate. And the last one is another AND gate, which we'll put it here. And what's attached to it? Q2 naught, which comes from here. And the other option is what? X, which is right here. So if I go and just play with the clock in this switch, and you attach this to the first LED, the one on the left, this is your second LED, you attach it. You know how we have the 8 LEDs on the top, 1 and 2, and you play with the switches, you'll see the light flickering based on where you are, which one of these is lit, and what is X, 0 or 1. So if, for example, if you see this is on and that's off, that's 1, 0, and X is 0, it will go to where it's supposed to go. If this is 0 and 1 and X is 1, you'll know where it's supposed to go. So you only have one input really, and that's this and whatever the state you're at.
I have a weird question.
Yes.
In a D flip-flop,
Yes.
does, if there's no charge to S and R, the inputs, does it output, if using NAND gates, does it output ones, or does it need that charge?
First, let me just, before I even answer the question, it says D flip-flop, right?
Yeah.
And you said SR.
Yeah.
There's no SR in the D flip-flop.
No, in the book it has inputs S and R.
Set and reset, I think.
Yeah.
Okay, set and reset will override everything. So it doesn't matter what D is.
I know, but if there's no value, if there's, say, a ground to
Yep.
0 and, or S and R, set and reset.
Yep.
It, complements the whatever input is there.
What you?
Would it be output to just to 1? Or?
I'm not sure if I'm following you, but let me show you what you have to do with them. Like let's say we have something like this. This is a D flip-flop with clear and pre. That's the same as set and reset, you know? Clear means make it 0. That's reset. And
Clear in the
So this case, if you wanted to clear it, you make that a 0. If you wanted to set it, preset it, you make that a 0. You do not put them both zeros. Can't be both zeros.
If you
So,
want to be one or the other.
no, they can be both ones. If you make them both ones, they have no effect on the circuit. Actually, when you go to use the flip-flop, if you don't want to use these guys, you need to make them 1. Because if you look at the truth table here, when they're 1, that's when you can use it actually. When this one is 0, it's going to clear. It doesn't matter what D is. When you make it 0, that's going to clear, which means it's going to make Q 0, regardless what D is.
Yeah, but 0 and 0 through NAND gates would complement it, right? So therefore the
Where's the NAND gate?
No, I'm just.
Yeah, it doesn't matter, because this, once you put a 0 here for the clear, it doesn't matter where you attach it. You can have an AND gate, OR gates, 10,000 gates. Once you make that 0, it doesn't even pay attention to that, it clears that, it makes it a 0. Once you make that a 0, and this is not 0, this is 0, it's going to set it, make it 1, regardless what D is. Gates, no gates, doesn't matter. If you want to use this, and you don't want these guys to be any factor, then you make them VCC. Once you make them VCC, they're no longer a factor, and everything depends on what you attach to D. But that's why you see the S and R on them. That's for set and reset, or preset and clear. Reset means clear it, make it 0. Set means make it a 1, or preset it to 1. And for this particular one, it's not always 0, but for this gate here, notice that's 0. Just like if you look at the clock here, there's a bubble before that clock. That means the clock works on the trailing edge when it goes from 1 to 0. That's when it looks at it. The only time it doesn't look at it, when you clear this. If you clear this, doesn't matter when you clear it, boom, it goes to 0. If you preset this, doesn't matter what the clock, boom, it goes to 1. But once you make them 1, then nothing will happen until the clock starts to fall down on the trailing edge. Hopefully I answered that question. Now, I could have done this problem with JK, I'd probably have a nicer one. This is actually not a bad one, but to go to the lab and hook that, you go, why can't we build this one? That doesn't seem like that complicated. Well, let's think about it. There's one board, there's another one chip, and there's another chip. There's 2. You have how many AND gates? 1, 2, 3, 4. Boop, perfect. That's another chip. I can get one that has 4 of them on it. That's 3 chips. How many OR gates? 2. Yep. I have one that has 2 of them on it. 2, 3 inputs. I can use that. That's 4 chips. Oh, I see a NOT gate. That's another chip. So on that board, you have how many chips now? Already 5. Yeah, just with that little design. 5 little chips lined up. You got to power every one of them. You got to ground every one of them. You got to make sure for the flip-flops here that preset and set are, you tap maybe lower to 0, then connect them to 1 to make sure it's no longer a factor. So you got a lot of connections going on. So just to connect this in the lab, you'll see probably about 100, 150 wires going through it.
Is
Well,
the clock in its own chip?
Is what?
Is the clock in its own chip?
No. The clock is actually, we don't have, you have an external clock on the device you can use. There's these switches. You could be the clock yourself if you want to. You can be the person, the clock going up, down, up, down. If you let the clock, there is a clock actually on them, on the board. And it's a decent speed. It's not really high speed. Because if it's like a computer chip, you and I will never see it.
It would just look like a solid.
Yeah, because you're talking about 2 gigahertz, 3 gigahertz. Yeah, good luck seeing it. Done. There's a million of them, you know? So we use the clock. We use one of the switches as a clock so you get to see what's going on. So that's what you're going to see in the lab today. You are actually going to be the clock moving that switch up and down. Let's see if it works on the rising edge. No, it doesn't. Let's see on the falling edge. If it's 1, it's 0. Let's see what's going on. We're going to do a timing diagram and see if the flip-flop that we gave you behave that way or not. You know. Sometimes you have a circuit that wouldn't be bad, like everything like this feeds to that, no gates. That would be easy to build, but it's not often, you know. I have another one mind, but the one mind is going to take a little bit longer, so we'll head to the lab now, because I have a feeling we'll be there for a while. I was about to create one that will count by 3s or by 4s. I'll do that next class.